So here's a very simple question. Well, who voted for Obama in 2012? And then there's this very fancy subtitle called Ecological Inference, and we found out that what we did was called Ecological Inference after we did it. So the two people who did the actual work are Seth Flaxman, who is going to Oxford for his postdoc, and Yu-Xiang Wang, who is currently renovating a house. Okay, so that's why I get the pleasure of being here. So here's the very, very simple problem that we're trying to solve. So let's say you have aggregate statistics. So maybe we have a district where the majority of people voted Republican. So 2,200 voted Republican, 1,300 voted Democrat. And it's a district where there are more women than men, 1,500 versus 2,000. And the idea is, well, can we use this information to fill in where the question marks are, right? This is the very, very basic, simple question that we're trying to solve, except that we have not just one electoral district, but many, and except that we actually know a fair amount about the distribution of individuals in the district. Of course, we don't know what they voted because voting is secret, but okay, we get this. So here's the simplest thing you could do. You could say, well, of course, not more than 1,500 men can vote Republican because there's a total of 1,500 men, right? Likewise, not more than 1,300 because there are not more than 1,300 votes for Democrats, and so on. If you have that, you can then amplify those bounds by getting corresponding lower bounds. It's 200 and 700. And in the other case, well, you don't get any lower bounds. And this is actually something that was proposed in 1953. And you would probably agree with me that this isn't terribly satisfactory because the bounds are incredibly loose. There are some cases where this actually works really well. So there's an algorithm called counter-braids for sketches where exactly that trick is used to recover things exactly. But in most of the cases, it doesn't work. So this is a tricky problem. It's more tricky because when you do aggregation and deaggregation, things can go horribly wrong. So here's an example of what can go wrong. It's called Simpson's paradox. And given that Donald Trump is so popular, let's just assume that we want to gauge the approval of his hairpiece by Republicans, Democrats, right? And, well, so let's say the Republicans overall like the hairpiece more than the Democrats do, but most men vote Democrat and most women vote Republican. Okay. Actually, that's not the case, and we'll get to that later. But the question is now, what would happen if we were to integrate out over men and women and just see the aggregate rating? And of course, if you've ever seen Simpson's paradox before, you would see that horrible things can happen. All of a sudden, we get the conclusion that actually Democrats like the hairpiece more than the Republicans do. So aggregation can mess up things rather badly. Furthermore, if you just use marginal attributes and you try to regress on that and do that in anger, things can go horribly wrong. So this was actually presented as evidence in court for electoral fraud. Namely, what they did is they used a very bad mathematical model to infer what fraction of blacks voted Democrat, and they got percentages more than 100%. And the logical conclusion for the person who did this was not that their math was horribly broken, but that, of course, the blacks must be committing electoral fraud. Right. Okay, so we don't want that. So the question is, can we design methods that are a little bit less crazy than this, that actually work, and then can we verify this? So that's essentially the task of this talk. So I'll start by defining exactly what data we have, what we're going to do. Then I'll talk about distribution regression, so mean maps, FastFood, Gaussian processes, and then in the end, of course, I'll conclude with showing you that this stuff works. So the data that we have is, on one hand, electoral data. So that basically means on a per district basis, and there's 700 of them or so, you actually know what fraction of people voted for Obama or Romney or whoever else, right? So that's after all the voting tallies, and those are well known. Secondly, we also have information about the demographics of people on an individual basis in those districts. Not necessarily a full sample, but a reasonably good subset. So like race, education, income, occupation, time to travel to work, and so on. So these are about 223 variables. And of course, nobody told us how this actually relates to their electoral preferences. But the idea is to use this distribution in combination with the electoral outcomes to infer how different subsets of the population actually did this. Well, things would be super easy if we had, let's say, 2 electoral districts, one with only women, one with only men, and we'd get their voting tallies, and we could figure this out exactly. But of course, within a year, they would probably get married between each other, so the next year this wouldn't work anymore. So we basically need to deaggregate. So here's what this looks like in practice. So let's say we have electoral results from 67 counties in Florida. And the problem is that the electoral districts and the regions for which this so-called PUMA data, public use microdata area and subsets, so that those mappings don't quite match each other. This is due to a number of reasons. First of all, when you actually generate this microdata, you care about practicality and representativeness and all that. On the other hand, if you're a politician, you care about gerrymandering. So this is, I think, a word that I've only encountered in the United States, and it's basically the well-practiced strategy of changing electoral boundaries in such a way that your candidate of preference wins. So, for instance, if you look at Austin, Texas, which is weird and Democrat, and the outskirts, which are nicely Republican, what happened is that the good politicians of Texas partitioned Austin like pizza slices to make sure that no Democrat ever gets voted in. Yeah. So the problem is you need to get this mapping right. And there's a couple of very nice tools from political science. We use the ones from the University of Missouri to get this mapping. And this reduces the resolution of electoral counts a little bit. So we end up with about 837 regions with census data from 11 million individuals. Okay. So this is all and well. But how do we actually know that our algorithm works? Well, we have something that's pretty decent. It's not perfect, but decent, namely ground truth exit polls. So what happens is that, people would stand outside the electoral booths and ask them, what did you vote for? And then ask them, how rich are you, how old are you? And yeah, they obviously wouldn't ask the gender because it's obvious. But the point is, they would get some of this information. It may very well be biased because you might not necessarily want to admit that you voted for Trump, right? But it's about as good as it gets. So our goal is, first of all, to come up with estimates that are basically as good as what the exit polls do. And what we'll do in the end is we'll compare to the exit polls. Secondly, to fill in for all the other states where these exit polls didn't exist, because they are very expensive. They're also super intrusive. So how do we do it? Right? It's actually very simple. If you think about it, what we have is we have per district, per region, we have a distribution of demographics. So we basically have sets of attributes, and we have a score. And so now what we simply do is we regress from the set of attributes to the score. So just some mapping, except that the argument now is not a single individual anymore, but the distribution over them. Now, this is actually a very old trick. We proposed it in 2002 as an extremely simple hack, and we had no idea that it was actually something principled. And then it took us a couple of years to realize that this is actually something that's principled and well designed and all that. And the point is essentially what you do is you map a distribution to the expectation of that distribution in feature space. And if these features are high enough dimensional, then everything's good and you can actually uniquely identify the distribution from it. You can do that with distributions. You can do that with sets. What you simply do is you compute the features for each element in the set and you average. So and there's lots of beautiful theory for that. Now, once you have those features, well, you can define a kernel. A kernel is simply the inner product between those feature maps. Right? Fairly straightforward. Now, once you have a kernel, you can pull out your Gaussian process hammer and you just do inference using Gaussian processes. Fairly straightforward. Why would we use Gaussian processes? Because in doing so, we can do things like get confidence intervals. We can do model selection. We can select kernels, all those things. So what happens here is, let's say we have those three regions, and we want to find out what the women in this region thought. Well, all we do is we just take the average now only over the demographic subsets that we care about. And so rather than looking at the statistics for the whole district, we look only at the women, and we try to evaluate accordingly. Okay. So what's the objective that we pick? Well, we just take a binomial logistic link function, because we don't only have one vote, we have thousands of votes, but that's fairly straightforward. We then take a Gaussian process, and the tiny little detail that I forgot to mention is we don't only take inner products between the demographic attributes, but also spatial attributes, like people in the South vote Republican, and we should be able to exploit that. And then you just throw all of that at, for instance, something like GP stuff, which is a very nice Gaussian process package, and you're done. A couple of details. You go and standardize the coordinates. You do a one-hot encoding for discrete attributes. And then for the location, we use something that's state-of-the-art 1950s or so, or maybe 40s, namely the Matern RBF kernel, and you're done. One minor detail. To actually deal with the RBF kernels efficiently, we use FastFood. This basically gives you an approximate high-dimensional mapping, and this way we don't have to deal with an 11 million by 11 million matrix, but only with a 1,000 by 1,000 matrix. Makes life a lot easier. Okay? And that's it. So it's completely standard. Now, how does it actually work? So the first obvious thing is, well, let's check for men versus women. And what we did here is we compared on those two pictures, in the case of men and women, the predictions that we get through ecological regression and the exit polls. The lightly blue shaded area are the confidence intervals that we get from our Gaussian process estimation, and lo and behold, well, statistic works. So this is actually kind of nice. And the points that you see here are basically the 20 states for which we have exit polls. Now, you can do much more fun things, because you can actually do a much finer deaggregation, which you couldn't even do with exit polls. You can ask on a per district basis. So for all of those 800 districts, well, what's our estimate for what fraction of women voted for Obama versus what fraction of men voted for Obama? And we take the difference. So this way we basically integrate out over all the local preferences, whatever, and we just look at the gender difference. And it turns out that, well, overall women like Obama. This had a lot to do with the different campaign messages and so on, but, they preferred Obama over Romney. Now, can you do other interesting things with this? Well, the obvious thing that we started out with is we can actually go and complete the exit polls. So, and, well, of course, we don't know whether they are true. The only thing that we could do is, as said, basically look at those pictures and infer from that that wherever we have data, we are pretty good within our confidence intervals, and then you can use that whenever you don't have exit polls. So it's better than having nothing. Okay. So last but not least, well, let's look at a couple of other statistics. So for instance, you can look at things like age. And we've stratified by 4 different age groups: 18 to 29, 30 to 44, and 45 to 64, and then retirees. And what you can see is that for the last 3 age groups, this works extremely well. So basically what you can see is that all the predictions versus the actual measurements are more or less within the error bars. Okay, that's what you would expect for an algorithm that works. Trouble is, for the really young voters, 18 to 29, we considerably overestimate the number of Obama votes. And this was quite troubling. So if you look at the table down there, this is basically just in intervals what you're seeing up there. Basically, something that's to the left of this blue line means we overestimate. To the right, it means we underestimate. But actually, if you look at the percentage of residents versus the percentage of voters, you can see that really young voters don't really vote that much. So they are underrepresented among the voters. And we have pretty good reason to believe that this is one of the reasons why basically we overestimated the effect, but they didn't really show up that much in the polls. If they'd actually voted as many as what we had otherwise, we would have probably been more correct. Because if you, for instance, look at the group of 30 to 44, well, they are substantially overrepresented. Okay, so now to conclude, what I introduced here is an algorithm for ecological regression that is very, very simple and easy to do. you really just take off-the-shelf tools, GP stuff, FastFood, a couple of other methods. But it actually fills an important gap in the political literature, because now you have some tools to at least estimate and de-aggregate within the districts what can be done. And so, of course, the creepy aspect of this is you can actually unmask some of the things that were based on merging surveys. So this immediately raises some differential privacy questions. You know, how can you actually safeguard it against things like that? There's a lot of related tools. So, for instance, you can go and estimate labels from label proportions, and Cook and De Freitas were some of the first ones to suggest that. You can look at bounds based on summary statistics. So Gregory Druck has done, and Andrew McCallum have done related things like that. So there's a lot that can be done. Of course, there are plenty of applications beyond, let's say, political science. So, for instance, a very fun application would be the following. If somebody had the data, well, you can't really administer drug tests to everybody at random, right? People don't like that. But what you can do is you can measure in the sewage what the percentage of various drugs is. So this way, you're basically giving an entire neighborhood a drug test. You also know the demographics. So based on those two pieces of information, you can then actually infer who is likely to take drugs. So there's a lot of applications beyond political science. And yeah, basically, well, have it and, well, use it. Okay, that's the end of my talk.
Thank you. We do have time for a few questions.
So I do have one question. So you're mapping this to the exit polls, but presumably we have better data after polling is done, and there are some statistics that many places provide post hoc after the election. Did you try to map to those as well and see how well you did to the actual final numbers?
So I'm not sure what other data. So if there's other data, we weren't aware of that. We thought exit polls was pretty much the only reliable information that you had on an individual basis. If that exists, well, let's talk after that, because this would actually be quite exciting, right? So the other thing is, I mean, of course, you could use exit polls to calibrate the algorithm further. So if you only care about inferring things for the remaining states, right, rather than the 20 for which you already have data, you can basically use the exit polls for additional model selection. So this would overall improve accuracy, but yeah.
Any other questions? Any questions?
Did you already get contacted by some political party?
Actually, yes. It's the Democrats. They probably like math more.
Excellent. Well, thanks again, Alex.